Okay, everyone. Now we shall begin our next talk. This talk is given by Professor Annika Heckel. He is from the Uppsala University. She will give us the talk about the chromatic number of random graphs. Let's welcome.
So thank you for the introduction. It's wonderful to speak at this meeting. Okay, so this is a talk about random graphs. So I should start by telling you what I mean by a random graph. So a random graph, in the broadest sense, is a mathematical model of a network. So you might think of this as a street map or a social network or the internet. So you start with n vertices, so n dots, and somehow randomly you draw connections or links between the vertices. And we call those random connections the edges. Now you could think of all sorts of ways how you might create such a network, like how you distribute the edges. So for the purpose of this talk, by a random graph, I always mean the Erdős random graph. Maybe I'll write down the definition here so you can keep it in mind. We call it GNP. It's kind of the most, the most fundamental and most basic random graph model. So we have n vertices, and we include every edge independently with probability p. Okay. Now, typically, we let the number of vertices tend to infinity, so we're looking at a very, very large graph. And often, but not always, we let the edge density p tend to 0 at some rate with n. And then we're interested in properties which hold with probability tending to 1 as n tends to infinity. So maybe let's also write this down. So this means with high probability, so with probability that tends to 1 as the number of vertices tends to infinity. All right. So the main topic of this talk is concentration in random graphs. Okay, so we're looking at our random graph, and we study typical properties that we might be interested in a graph. So, for example, how well connected is it? How many steps do I need if I go along edges to get from one vertex to the next? If the graph is not connected, then maybe how large are the connected components of the graph, and so on. Another graph parameter that we could look at is the size of the largest clique in a graph. So a clique is a graph like this, where everything is connected to everything else. And so the kind of underlying question when you think about concentration is how randomly does a graph parameter really behave? What do I mean by this? So concentration is a phenomenon that we see all the time in random graph theory and also in probabilistic combinatorics. So we have some graph parameter, and it can take many values. This is supposed to say many values in principle, but it's very likely that it's contained in some short interval. So, for example, the size of the largest clique, which we have up here. In principle, if we have a random graph, it could be that there are no edges at all present. That's possible. And then the largest clique has size 1. And it could be that all the edges are present, and then the largest clique has size n. So it can be, in principle, anything between 1 and n. But in fact, if we look at the random graph Gn1/2, where every edge is present independently with probability 1/2, so every edge is a coin flip, then in fact, it is very likely that we know exactly what the size of the largest clique is. So there's some some function which I didn't write out all the way because it's not so important what the function is. But with high probability, the size of the largest clique in Gn1/2 is exactly this function alpha of n, even though it could in principle be anything between 1 and n. Okay, you will notice that here I put in 1/2 for the edge density. This is because the random graph Gn1/2 is kind of special, and we will see it in this talk a couple of times. So of course we have edge density 1/2. And if you think about it, this is the same thing as drawing a uniform graph on n vertices. So we could also generate this graph by saying pick a graph on n vertices uniformly. So from all possible graphs on n vertices. So that's another, and this is why people are interested, or one reason why people are interested in Gn1/2, because it's the same thing as putting all the graphs on n vertices into a bag and then drawing one out at random. Okay, and actually, I mean, it's NP hard to find the clique, like the size of the largest clique on a graph in principle. And still we know if we pick a graph uniformly at random on n vertices, with probability tending to 1 as n is large, we know exactly what the clique number is. But finding such a clique would be a very hard thing, or even finding a clique that is nearly that size. So I find this quite extraordinary. Okay, so you saw in the title I also, I'm going to talk about the chromatic number. So this is a graph parameter that's also quite fundamental. And it can be defined in several ways. So the following is my favorite way of defining it. So we say that a graph is bipartite if we can split up the vertices into 2 groups. We can partition the vertices into 2 groups. And all the edges have to be between the 2 groups like this. So we can't have any, and all the edges have to be between the 2 groups. So we can't have any edges in here. So this is a bipartite graph. You can then also define a tripartite graph if you can partition the vertices into 3 groups like this. And the edges are only allowed to go between the groups, and that's a tripartite graph. And so on. This would be a 4-partite graph. And in general, you can look at an R-partite graph, where you have R parts, and the edges are only allowed to go between the parts. And now the chromatic number is the smallest r so that you can do this. The smallest r so that G is R-partite. So this is the same thing. So there are 3 different definitions that I might use in this talk. So this is the same thing as saying smallest r so that I can partition the vertices into independent sets. And now the most standard definition is the smallest number of colors so that I can give a color to every vertex. So that neighbors always get different colors. By neighbors, I mean 2 vertices connected by an edge. So I've already suggestively given the different parts different colors. So this would be the coloring that is used here. So if you've done an undergraduate class on random graphs, you will have seen, on graphs, then you will have seen this definition, and that's why it's called the chromatic number. Okay, so yeah, so the chromatic number appears throughout combinatorics. Maybe the most famous result about the chromatic number is the four-color theorem, which says that if a graph is planar, then it has chromatic number at most 4. And it also appears in applications. So the typical example is a research allocation or a scheduling problem. Okay, so let's get it back to our random graphs. Okay, so what can we say about the chromatic number of a random graph GMP if we draw every edge independently with probability P? I mean, this is a very general question. Now, if I draw a random graph and then I calculate the chromatic number of that, that's of course a random variable. So what I should say is, what can we say about the distribution of this random variable? So there are kind of two main directions into which results about the chromatic number go. One is, what can we say about the typical size of the chromatic number, the typical value? Can we maybe prove upper and lower bounds that hold with probability tending to 1? And sort of the other main direction is, what can we say about the concentration of the chromatic number? What can we say about maybe the standard deviation? So basically, if we generate the random graph a couple of times in a row, and each time we calculate the chromatic number, how close together are the results going to be? Are they going to be all over the place? Or if we've done this once and repeat the experiment, do we expect something close to what we got the first time? So let's first briefly talk about the first question. So there's a famous result by Bollobás from the 80s, who was the first to find the asymptotic value of the chromatic number of Gn1/2. This was improved a couple of times, and the best bounds, not anymore the best bounds, but the best bounds up until a quite recent result was the following result from my PhD thesis, where I had upper and lower bounds which kind of match. So the upper and lower bounds are, of course, always with probability tending to 1, and they match up to a term of this size. And I'm mentioning this result because it will become important when talking about the concentration later. So this is not what the talk is about. Okay, so how about concentration? Well, you will notice that these upper and lower bounds are, of course, already a weak concentration type result, right? This gives us an interval, an explicit interval, that we know contains the chromatic number with high probability. But it turns out that if you don't have to be explicit about the interval, you can do a lot better than this. You can make the interval a lot smaller if you only have to prove an interval exists, but not spell out what the interval is. What do I mean by that? So there's another famous result, also from the 80s, due to Shamir and Spencer, who showed that for Gn1/2, and in fact for any p or even any function p of n, the chromatic number of GnP is always contained in an interval of length at most about √n. So we know there's, well, I say an interval, by that I always mean a sequence of interval, one for every n, and with probability tending to 1 as n tends to infinity, the chromatic number is in this interval. And it's kind of an annoying feature of the method used in this proof that we get no information at all on how to find these intervals. So this does not help us at all to find out the size of the chromatic number. But we know these intervals exist. They have length at most √n, and they contain the chromatic number. Okay. Now, this is a very general result, which holds for every p, and in fact for every function p of n. Of course, depending on the function, the intervals will most likely be different. If p is small enough, you can improve this considerably. So, okay, for our favorite random graph, or my favorite random graph, Gn1/2, We can improve it a little bit. We can kind of win a log factor. But if p is less than n to the minus 1/2, then it was shown by Alan and Krivelevich in 1997 that in fact you have 2-point concentration, meaning we actually have 2 consecutive values. So this is almost deterministic behavior. 2 consecutive values so that the chromatic number takes one of these 2 values with high probability. And actually, most of the time it's just 1 value, but it's always stated like this because as you increase n, sometimes it can be up to 2. Okay, so this is quite strong concentration, perhaps surprising the first time you see these things. Now, as I said, this method up here doesn't give us any information on what these, or this is not the same method, but again, this result gives us no information what these 2 values are. So for some special p, we know also what the values are. So in particular, if p is some constant over n, then we know 2 explicit values for the chromatic number. So we can write out 2 values, and the chromatic number with high probability takes one of those 2. And this was extended to 3 explicit values up to edge density n to the minus 3/4. Okay, so let's summarize what we know. Okay, so for the value of the chromatic number, we have approximate results basically everywhere, upper and lower bounds that hold up to some accuracy. So this is, here I'm drawing I didn't label this axis, this is p of n. Okay, we have a very general result that says the concentration is almost always at most root n, so there are always some intervals of length at most root n that contain the chromatic number. Up to a certain point, we know actually this can be improved to 2 values. We have 2-point concentration. And we know what these values are, more or less, up to n to the minus 3/4. Also, it's kind of for trivial reasons, it's clear that as you let p tend to 1 quickly enough, or at the right rate, you don't have 2-point concentration anymore. So in some range, for sort of silly reasons, this root n is actually sharp. We're going to be here for the remainder of the talk at p equals 1/2. And in particular, look at the concentration behavior here. So it's an old question due to Bollobás, who asked, okay, we have these very sharp upper bound, we have these very general strong concentration results. We know lots of cases where the chromatic number is concentrated. Sometimes we know on what it is concentrated, sometimes not. But up to, yes? I'll get to that in a minute. So I'll answer you in a minute. So Bollobás asked, we have all these results showing that the chromatic number is concentrated. Do we have anything in the other direction? Can we show that the chromatic number for GNP, for any p, or GN 1/2 is not concentrated on, let's say, a constant number of integers, or in this case, 100 consecutive integers. So what's 100 consecutive integers? Okay, so n plus 1, n plus 2, and so on. Okay, so I could also have said an interval of length 100, because the chromatic number is always in a whole number, in an integer. So this is... yes, you're absolutely correct. I should say k, because Okay, we start with some integer k, and I guess I should go up to 99. And then we have 100 consecutive integers. Oh, so, okay, so this is an interval of length 100. Okay. So this is kind of phrased in a, he's trying to phrase the question in the most, kind of the weakest way you could show non-concentration, right? We know it's concentrated on at most, like we have an upper bound on the interval length root n, and he's asking, can we find anything at all from the other side? So can we show it's not concentrated on constant length? Can we show it's not concentrated on length 100? Or for any other p, are there non-trivial examples where you can show that the chromatic number is not concentrated? So he's even saying, yeah, the weakest results, such as this one, would be of interest. Okay, so, and now I'll come to the main result of this talk. So this is a theorem from 2019, which says that the chromatic number is not contained with high probability in any sequence of intervals of length about n to the 1/4. So not 100, and in fact, not n to the 1/4. Now this is a correct statement, but it's kind of important, the order of quantifiers. So I spelled out more formally what I mean by this. So I mean that for any constant epsilon, if we have some sequence of intervals that contains the chromatic number with probability tending to 1, there are infinitely many values n, so that the interval length is at least n to the 1/4 minus epsilon. Note that this result does not say that every interval is long, just that there have to be long intervals somewhere in between. And this is kind of a curious feature of the method that's used to prove this theorem, which I hopefully will get to talk about a bit later in this talk. Okay, so we have this kind of lower bound, at least for some n, of n to the 1/4. So sometime after this paper came out, jointly with Oliver Riordan, we were able to actually push this up to n to the 1/2 minus epsilon. So if you recall, the upper bound on concentration is n to the 1/2. So this kind of is almost there from the other direction, at least for some n. So this is the kind of by the same method, but extended in some way. And then still using the same method, but with a lot of calculation, and also using as an ingredient a new result of myself and Konstantinos Panagiotou from last year. We can actually push this all the way here, and we think this is as far as this can be pushed, actually. So we actually think for some n, this is the correct answer. So at the end of the talk, hopefully I can talk about some conjectures on what we think the correct concentration behavior is. So these are lower bounds for some n, right? And later on, I want to share some intuition on what the answer is, and maybe a spoiler, we don't think it's the same for every n. So we don't think this is the answer for every n, but we think it is the answer for some n. Okay, so if you compare this now to the best upper bound, which I mentioned earlier, we're now, for these special n, only a log factor away. Okay. So these are the results. So let me talk a little bit about the method, because I think the reason why this remained an open question for quite some time is that we don't have many methods to prove, to kind of get lower bounds on the concentration of a random variable. So we have a big toolbox to get upper bounds, upper concentration bounds, but we don't have very much coming from the other way. So let me first talk about the general structure of the argument that gives you a lower bound on the concentration interval length. So the general structure is the following. We have, the proof needs two ingredients. And the first ingredient is actually, well, it's actually a kind of surprisingly a weak concentration type result, namely some upper and lower bounds that contain the lower bound and upper bound for the chromatic number that differ by some term delta. I'm not spelling out what any of these functions are at the moment, so please ignore that you don't know what f is and that you don't know what f delta is and alpha and so on. And I just want you to understand the structure of the argument at the moment. Okay, so we have upper and lower bounds. So we have some function f of n. This is an estimate for the chromatic number. So we know we've proved somehow that the chromatic number is contained in this corridor. And we need a lower bound on the slope of this function. Maybe I should start using colors. So you can still see something in this picture. Okay, so this has slope at least 1 over alpha, where I'm still not telling you what all the functions are. Some function 1 over alpha plus some leeway. Okay. Okay. And the second ingredient is a coupling result where we compare the chromatic numbers of two different random graphs. So one is g and 1/2, and the other one is g n prime 1/2, where n prime is slightly larger than n. So we increase the number of vertices, and we compare the chromatic numbers of these random graphs. And we now need a coupling, so we generate the two random graphs together, so that as you increase n, the chromatic number increases by at most r with some constant probability. So I could have written 0.01 here. As it happens, we have it with 1/4. Okay, so, and this is the same, like, again, you don't need to know what all these things are, but this is the same alpha as this alpha. So what does this say? This means that if we have some sequence of intervals that contain the chromatic number with high probability, one for n, Sn Tn, and one for n prime, Sn prime Tn prime, then these intervals can be at most, like the difference between them can be at most r. Because with probability close to 100%, the chromatic number of Gn 1/2 is in here. The chromatic number of Gn prime 1/2 is in here. And with probability at least 1/4, they're at most r apart. So this difference can be at most r. Okay, good. So now we have these two ingredients. What do we do with them? So that's best shown by a picture. This is just this picture. Okay, now suppose you have lots of intervals, which I'm drawing here, kind of small intervals that contain the chromatic number with high probability. Then the coupling tells us, okay, if I go to the right by alpha times r, then we can go up by at most r. So the slope of this red line here is at most 1 over alpha. Because I go to the right by alpha times r, and I go up by at most r. Okay, but the slope of the big line up here is bigger than 1 over alpha. So this increases more than these red lines. And so you can see if all the intervals are short, eventually you get to a contradiction, which is this interval. So if this keeps going on like this, all the intervals are short, then this will only go up by a slope of at most 1 over alpha. This will go up by a higher slope. And then we will get the contradiction that this is an interval that contains the chromatic number with high probability, and this is also an interval like this, and they don't intersect. So that's a contradiction. Okay, so this is the kind of backbone of the argument. Okay, so this means this can't happen not all intervals can be short. There has to be at least one long interval every now and again, so you don't get this contradiction. And probably it's not the case that all the intervals are short and then there's a giant interval every now and then again short intervals and a giant one. Probably all of them are reasonably long. But the method only gives us that every once in a while there has to be one long interval. Okay. Let me see how I'm doing on time. Okay, I should actually hurry up a little bit. I didn't tell you what all of the functions are. So the important one, of course, is this function alpha of n. So let me tell you what this mysterious function is. This is the independence number of the graph, basically. So the independence number of any graph, not a random graph, is the size of the largest independent vertex set. And now for the random graph g and 1/2, actually we know exactly what it is. It's essentially the same thing as the clique number I told you about earlier, because it's symmetrical. Yeah, that doesn't matter anyway. So for g and 1/2, we know basically is exactly what the independence number is. So the size of the largest independent set with probability tending to 1. We have an independent set of this size rounded down to the nearest integer, and no larger ones. So what does this have to do with colorings? So if you go back to the definitions of the chromatic number, so the chromatic number is the smallest r so that we can partition the vertices into independent sets. Okay, so, and if all of these independent sets have size at most alpha, then we immediately get a lower bound on the chromatic number. The chromatic number is at least number of vertices divided by size of the largest independent set. You can't do better than this in general in any graph. And I can rewrite the bounds we had on the chromatic number earlier of g and 1/2 in terms of this function, alpha 0. And it turns out that the chromatic number is very, very close to this lower bound. So we can color the graph so that on average, our color class size is about alpha minus 3, alpha minus 4. So we have the optimal coloring on average uses very, very large color classes that are sort of close to the maximum. And so the main intuition is now that an optimal coloring, there are only a few of these very large maximal sets, and an optimal coloring probably uses all or almost all independent sets of size alpha as color classes. And we can count how many of these there are. Let's call this x alpha, the number of independent sets of size alpha. So set of size alpha I'm abbreviating by alpha set. And since these sets, they are of logarithmic size, so most of them kind of pop up independently in the graph, we can actually say a lot about the number of independent sets of this size. So by the Chen-Stein method, we can show that actually the number of these very large independent sets have roughly a Poisson distribution. So we know how much that fluctuates, the number of available maximal independent sets. And so the chromatic number should, if we use all of those in the optimal coloring, then the chromatic number, what we get in the end, should also vary about as much as the number of available alpha sets, at least. Okay. I think I might actually skip over. So I had some nice pictures, but I think I want to get to the conjectures, so I'm going to skip over the rest of the proof. Sorry. Okay, so there we are. So this is the intuition I just talked about. So an optimal coloring should contain all or almost all maximal independent sets as color classes. Their number is Poisson distributed, but the expectation of the Poisson distribution is not the same for every n. It varies between n to the 0 and n to the 1. So this kind of, I've run out of space here. Okay, so we can look at this more closely. So if we have an alpha set, so if we kind of, suppose we find an alpha set somewhere. So we found an independent set of size alpha. We take it as a color class. Then we've used one color, and we have to color n minus alpha other vertices. And now if we look at the estimate we have for the chromatic number, this is, by the way, the mysterious function f of n. This has slope 1 over alpha plus some term like this. So if we pretend that this term doesn't exist, like forget about it, let's say the chromatic number is exactly given by this, then if we only have n minus alpha vertices left, we kind of, this is how many, like if we go down by alpha vertices, the number of colors that we need should go down by the slope of this estimate f times alpha. But we've already used one color. So we should, if we find an extra alpha set, that should save us this many colors, right? Because alpha times this is 1 plus alpha over log squared. And the 1 cancels with the other one where we've used a color. So, and alpha is logarithmic, so this comes out as 1 over log n. Okay, so every time we find an alpha set, it should save us about 1 over log n colors. Now, the number of alpha sets, as I said, is Poisson distributed. And the expectation is n to the something, where the something goes from 0 to 1, like this. So as you increase n, this exponent is somewhere, like, this is where you have very, very few sets of this size. And then as you increase n, the size is logarithmic, so it stays the same for a long time, but the number increases. And here you have a lot of these maximal independent sets, almost n of them. And then as you increase n more, alpha plus 1 sets start popping up. So here, actually, the independence number jumps up to the next value. And this is why you have this discontinuity here. So these are the points where the independence number increases by 1. Okay, anyway, so you have this number of independent sets of size alpha, which varies by about this amount because it's Poisson distributed. And so the conjecture is, okay, the chromatic number should then not be concentrated on fewer than that many values, which is how much the number of alpha sets varies, divided by log n, because every additional alpha set saves you 1 over log n colors. So this is kind of conjecture 1 from this intuition. And in fact, if you go into the proof from the results jointly with Oliver Riordan, this is more or less what we show, except we don't show it for every n because the method does not give you anything for every n. So we show that, okay, for every n, unless we are very close to these jump points, so we can't be close to the discontinuity points, but for every n that's sufficiently far away from the jump points, there's some n star nearby so that this lower bound holds. Okay, so this is in detail our result. And then you get to the n to the 1/2 if you get as close as you can to this point, to these jump points, as close as we can push it. Okay, now just briefly, a similar thing happens, at least we think it happens, with alpha minus 1 sets. So if you go to the next size of independent sets, these are still Poisson distributed, only there are more of them, right? We had n to the theta before, and now the alpha minus 1 sets, there are n to the 1 plus theta of them, but they're still roughly Poisson distributed. The intuition can't be anymore that we use all of them in our coloring, because we can't use this many, we can't use all of them in our coloring, there are too many. We only have n vertices. And also they intersect. So we don't have them nice and disjoint like we have the alpha sets. So the new heuristic is now, okay, probably the chromatic number is close to what we call the first moment threshold, which is the smallest k, so that the expected number of k colorings is at least 1. Or at least the chromatic number maybe varies like the first moment threshold does. So if you look at this new heuristic, you can work out how much finding an additional alpha minus 1 set shifts your first moment threshold. And this is a long calculation, so this is, I don't know, 15 pages in our paper, but the result is every additional alpha minus 1 set gives you about, like shifts your first moment threshold by about this. Okay, so conjecture 2, and this is, like, we don't have this anywhere. The conjecture 2 is that the chromatic number is not concentrated on fewer than variation of the alpha minus 1 sets times benefit of an alpha minus 1 set values, which comes out as this term. So this is much nicer in the picture. So this is the lower bound from conjecture 1, and this is the lower bound from conjecture 2, and they kind of go like this. And if you plot it on a log scale, they actually go in straight lines like this. Okay, so, and here, this lower bound, we sometimes more or less have. We have for every n star nearby where it holds. Okay, so the question is now, can we continue like this? So do we now look at alpha minus 2 sets, alpha minus 3 sets, and so on? And we think the answer is no. And we have some evidence why the answer should be no. So basically, this is a result jointly with Konstantinos Panagiotou from last year. So if we only look at colorings that don't use these top 2 color classes, alpha and alpha minus 1 sets, you're only allowed to use alpha minus 2 sets and smaller in your coloring. Then actually something curious happens. The chromatic number is then basically 2-point concentrated. So, which maybe comes as a surprise because the value of the chromatic number is still very similar. But here you can use what's called the second moment method to actually get very, very sharp concentration. And this is why we think basically nothing else other than alpha and alpha minus 1 sets matters. So yes, this is what we call the Ziegler conjecture. So this kind of arose from the work of 3 separate groups over the years. So this is due to Bollobás, myself, Rob Morris, Konstantinos Panagiotou, Oliver Riordan, and Paul Smith. So the conjecture is that the chromatic number, the concentration of the chromatic number actually is described by the maximum of these 2 conjectured lower bounds. Okay, so this is the conjecture I wanted to show you, which I think is a very nice one. Now you can look at this in more detail. So we have some conjectures on what exactly the top of the zigzag is. We think it's actually exactly the thing that we're able to show for some n. I could go into the reasons why. So we don't just think this because that's what we can show. We have other reasons as well, and then we were able to show it. We have a conjecture for what exactly this is. And actually, you can read out a Gaussian limiting distribution for the chromatic number from the heuristics, which would be the most, like this would be the ultimate result about the chromatic number, basically, getting the whole distribution, and likely very hard to prove. Okay. Now, the final slide is some open questions, but I think I've run out of time, so I think I should stop here.
Okay. Now it's okay. That sounds good. Okay. Question?
Yes.
If p is a different value, not going to 1 or 0, just some fixed values, anything known, even rough estimates?
So this, like the lower bound n to the 1/2 minus epsilon, we actually have it also for every constant p. So I put in p equals 1/2, but it actually holds for every constant p.
Yes. What is theta in the last result?
The previous slide, you mean?
Yes.
Hang on.
Let's see. Higher.
Mm-hmm.
Higher. Oh,
This one. Yeah.
What is theta?
Yes. Theta is the. I had it on an earlier slide. So the expected number of alpha sets is n to the theta.
Okay. Thanks.
Okay, thanks, Professor Heckel again.
Thank you very much.
We will continue our section after 10 minutes. We will have a break.